Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am delighted to have Arianna Long with us today. Hello, Arianna.
Hi, Frank. Thanks so much for having me back.
Okay. Yeah, so she is now a veteran of two. We did one in 2020, uh,
Hmm.
back in, shortly after COVID started, I think is
That's
when.
right.
So, so welcome back. You must have some articles that appeal to me or something. So, which we will get to in a little bit. And you're probably in a different geolocation than you were in 2020. So, what is your current location?
That's
And
right.
say again.
That's right. Yeah, I just finished my first year as faculty at the University of Washington in Seattle. So it was quite a year. Last
Awesome.
time we talked, I think I was in California, but yeah, now I'm in Seattle.
Yeah, you could have been. Yeah. Okay. Yeah, yeah. Yeah, I was just up in Seattle like 2 months ago or so. I was at
Yeah, so not during the beautiful summer season, which is what we're entering. What?
No, no. I was visiting the INT at the time for some program they had, so I think it's one or two floors up from you.
That's right.
Yeah. Um, Seattle, Pacific Northwest. Has summer arrived?
Okay, so it has sort of started. So summer here is definitely different. I'm learning. It is defined by basically a lack of rain, not and it is warmer, but not hot.
Yeah,
Um,
right, right.
but yes, we are
That's
entering
a
a
great way
dry.
to answer that.
Yeah,
Defined by a
yeah,
lack of rain. Okay.
yeah. So we're entering the dry season. It's really beautiful, usually in the low 60s to mid
Yeah, nice,
60s,
nice.
maybe low 70s. Great gardening weather. I started
Hmm.
planting my vegetable garden. Do you garden at
Cool.
all?
What are you growing?
I am growing tomatoes, onions, lots of herbs, lettuces, and strawberries. I have a very vibrant strawberry bush. Yeah,
Awesome. Awesome. That
very
is
excited.
fantastic. Very good. And it is May 27th of 2025 as we record this, and I'm in Phoenix, and we are definitely in our summer hit. So we're exceeding the triple digit Fahrenheit here
Wow. Do
regularly.
people garden there? I mean, it must be super hot. Do you use green?
If you like gardening cactus,
Okay.
succulents,
Yes. Yeah.
they do really well. Some trees do well. Palo Verdes tend to do really well. And there are certain types of plants that will thrive in
Okay.
such conditions.
Mhm.
But we won't be growing any strawberries. Takes a little cooler for that one.
Mhm.
Very cool. Very nice. Okay. And Ariana, what do you like to do for research?
Yeah, so I work on massive red galaxies in the early universe.
Okay.
I'm mostly an observer. I work a lot with simulators, but I am mostly an observer. So using multi-wavelength data, pretty much across the electromagnetic spectrum, but I focus on red galaxies, which usually means aged. So old stellar populations, so they can be read from old stars or they could be read from dust, so dusty galaxies as well. Um, and because nowadays, when you say early universe, that could mean wildly different
Things
things.
to different people, yes.
Yes. So I mostly focus on the Redshift 3 to 6 universe.
Okay.
The new language for that is cosmic morning. I like to sometimes say cosmic brunch, if you will.
I hope it comes with a latte.
Me too.
Very cool. Very cool. And that is going to bring us to this very awesome APJ article. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. Efficient NIRCam selection of quiescent galaxies at Z between 3 and 6 in CEERS. And Ariana, take us away.
Yeah, so first thing I'll do is give a shout out to my awesome co-authors. This is a technically a CEERS paper, and CEERS is a big collaboration of a lot of astronomers around the world, and they were one of the first organizations or collaborations to get early data from the JWST telescope. And so this was done with some of the first round of data that we got. And many of these people contributed to that data reduction, to validating, to testing some of the models in this paper. So I'm very appreciative to all my co-authors.
Great shout out. Great. And you're right, quite the international crew here.
Oh yeah. Oh
Very
yeah.
cool. Okay.
Mhm.
Let's go. Let's get into it.
Yeah, so okay, so essentially high redshift quiescent galaxies are really interesting for a variety of reasons. The majority of those reasons kind of center around their extremeness. So classically, when we think of galaxy evolution, we think of bottom-up hierarchical evolution where smaller galaxies merge together to create larger ones.
Right here.
And what that would mean is the most massive galaxies in the universe would likely be the oldest as well and would likely still be star forming locally today.
Okay.
But instead, we find the opposite, that a lot of the most massive galaxies that we see have been quiescent and have predominantly really old stellar populations that suggest that they form in the first about 2 billion years of the cosmos. Um, and
Mm-hmm.
so, yeah, so a few people put that together in the 2010s-ish and said, okay, well, if that's true in the 2000s, 2010s, if that's true, then there should be passive quiescent galaxies in the early universe as well that kind of maintain that status for the majority of cosmic time. So indeed, they did invest a ton of time, telescope time, looking for these red galaxies. If you don't know much about looking at red objects, in general, it's really hard to do that from the ground.
Yeah.
You're pushing into near IR wavelengths, and there's a lot of noise and atmospheric absorption with those wavelengths, and so it's very hard to do to
From the
find them. And so it would take sometimes 8 to 10 hours to confirm these sources, but they did
wow.
find them. Um, and so with JWST, what we were thinking is, in theory, we have these infrared bands, these near infrared bands in space that are really sensitive. Between that and all the other ancillary data we have, we should be able to find larger samples of these galaxies to understand how they formed so quickly, how they got so big, and then also how and why maybe they stopped forming stars. But the first step is to find
Yes.
them.
Yes. Okay. Let's find them first.
Yes.
We can theorize later, but let's find.
Yeah. First step, we have to find them. And so we have a lot of established techniques for finding these sources at lower redshifts. And those established techniques kind of rely on essentially you can see that J-band magnitude in the middle of that paragraph on the left.
Yeah.
They rely on this multi-wavelength detection, 3 bands, two to kind of straddle what's called like the stellar bump, where
Yes.
like old stellar populations kind of peak,
Yep.
and then a third band to distinguish between dust versus old star emission.
Uh-huh.
And because dusty galaxies are a large contaminant, again, due to that redness
Okay.
of the space.
Okay.
Now, the rest frame J band, when you redshift it to these epochs, is actually in the mid-infrared, so more like 7 microns-ish.
Okay.
Um, and so without that, that's MIRI right now at this point, or Spitzer IRAC. And
Mhm.
not a lot of these surveys have MIRI data because it's a smaller field of view. Nowadays, that's changed. It's been a few years, but in
Been
this
a few
beginning,
years.
there was a
Wow.
lot of NIRCam data.
Yeah.
Um, and so between that and the fact that these quiescent galaxies at high redshift are generally younger than those at low redshift, then they're slightly bluer. They're not as red.
Okay.
So what was happening is we were seeing a lot of missing quiescent galaxies using these older selection techniques that were more established for the lower redshift universe. We
Okay.
needed to come up with new ones.
Okay.
And so this is an attempt to do that. That's what this
Cool.
paper is, using existing NIRCam data to identify young quiescent, massive quiescent galaxies at high redshift,
Very cool.
using empirical data, not modeled J-band data that we don't have actual observational constraints on.
Right. Cool.
Yeah,
This is good. This is good. Okay.
yeah. So yeah, we have false positives. Again, a high contamination rate, a low success rate. And so if we push down a little bit more to that first figure, I can show you some
Yeah.
of the,
Go. Then we'll talk about
yeah,
this, but let's
I'll
go
talk
figure
about all
one.
that.
Let's see what we got here.
Yeah.
Okay.
Okay, great. So on the right-hand side of this figure, I have two kind of figures that show different galaxy SEDs. The one on top is predominantly dusty star-forming galaxies of varying dust attenuation rates.
Okay.
So you can see on the purple curves
Whoop.
on the right-hand side. Yeah. There we go. Yeah, I know.
Ah,
Not
okay. I'm with you.
um, so on the right-hand side, you can see the purple curves are dusty star-forming galaxies that don't have a lot of dust, just a little bit. And then
Hmm.
as you push down to the darker brown color, you have a lot of dust attenuation that makes this kind of red optical UV continuum.
Yeah.
Um,
Okay.
and then below this, Yeah, the trend, right? You can see how
Right,
it drops out. You
right.
start seeing some emission, right? We're in observe frame, so you can see the wavelengths. And again, you can see where the MIRI 7.7 micron band would be great.
Yes.
That's around where the J band lives for
Mm-hmm.
sources, but we didn't have that data at the time.
Right. At the time.
At the time.
Okay.
And so, and then on the bottom, I show some SEDs of spectroscopically confirmed high redshift quiescent galaxies just to show their shape as they redshift
Nice.
through redshift 3 to 6. So you can see again, there's definitely some reddening and some, decline of slope, missing those UV luminous young stars. And then,
Yes.
of
Yeah.
course, getting fainter as they redshift.
Right.
So
Okay.
then these were fed into the top left figure. We took these and essentially as we redshifted from 3 to 6, we did it in small steps
Okay.
and we plotted these two colors, the 277 or 2.7 micron or 2.8 micron
I'm
band
with
versus
you.
4.4 and the 1.5 micron versus the 2.8.
Yeah.
Uh,
Okay.
so the colors actually, the purple corresponds to the dusty star-forming galaxy, so you can see how they redshift and move kind of throughout this color space. Yeah, thank
Mhm.
you.
Yeah.
And then the dark red kind of triangles mimic the or follow the quiescent galaxies as they redshift through space.
Okay. Okay. I'm with you. Uh-huh.
Okay, great. And then those pink kind of circles are from
Yeah.
another quiescent galaxy sample
Mm.
for comparison.
Okay.
And then the purple circles are for really high redshift, like, redshift 9, 10, Mach galaxies with emission lines, because sometimes extreme emission lines can contaminate a wideband photometry and make it brighter than it really is at a continuum level and induce a fake redness between two bands.
Gotcha. Cool.
So
Okay.
a lot of contamination consideration here. And so after
Yeah.
over plotting all these different potential contaminants, I was able to kind of draw out this wedge space you see here that predominantly picks up quiescent galaxies and leaves out dusty star-forming galaxies.
Okay. Part of it is dashed.
That's right. Yeah. So I do offer in the paper a two different versions of this wedge, one with the solid lines and one extension into the dash line. And
Okay.
that's because the one with the solid line has the least amount of contaminants.
Contamination. Okay. Yes.
Mhm.
Okay.
Once you push a little bit bluer into that dash line, you do get more contamination, but you might get more completeness as well.
Right.
So it's a
Good.
dealer's choice.
Well, we'll see what that choice yields here in a little bit. Okay.
Exactly, exactly. And then the figure on the bottom left,
Yeah.
these are mock SED templates. So the ones on the right are empirical, they're real, they're observed. We wanted to also include some mock SED templates just to see if some of the model templates that we're using kind of hold up.
Hold up. Yep. Hmm.
And we show the dashed and yeah, so this is with dust attenuation. So if you take a quiescent galaxy and you add dust to it, how does it move in this color space? Because we can have dusty quiescent galaxies as well. Um, and so you can see here that in general, most of them tend to stay in the space, but a fair amount do kind of travel outside the wedge towards the dusty galaxy region, which makes sense. They get redder.
Yeah.
Um, and then you have the dashed and dotted lines.
Right.
Those correspond to different thresholds that we use in the literature nowadays for quiescence. So in the low redshift universe, we tend to use a more strict threshold, which is the specific star formation rate, which is the star formation rate divided by the stellar mass, kind of a normalization for a galaxy's star forming properties. Um, and so the -11 is usually a more traditional strict definition.
Okay. Okay.
But again, these high redshift quiescents are still significantly offset from the star forming sequence, so they are outliers, but
Okay.
they're technically oftentimes more post-starbursty. So they form very vigorously. They might still have a little bit of UV emission, but it's dying down.
Right.
And so that is what the -10 corresponds to. And we do want to incorporate those as
Little
well.
looser. Little looser. That's good. It's exploring the
Mhm.
boundaries, right? Whether you allow for a little bit more contaminants and otherwise.
Right.
Different
Yeah. And
definitions.
it
Different
just depends
definitions.
on
Yeah.
exactly. Yeah. It depends on your goals. I mean, some people are very interested in finding the oldest and most quenched galaxies, and they may not care about this method for that reason. But if you're interested in kind of capturing that transition from starburst to quiescence, and you want to capture galaxies in the intermediate phase so you can understand that process more, I
Yes.
argue that you need to capture more of those post-starbursty types.
Uh,
That is partially what is driven here.
I would not argue with that position. Okay, cool. Very good. I'm with you.
Yeah. It was a lot of fun playing with this. I mean, I tested a lot of different colors, but ultimately, these were decided on because they do mimic a lot of the same selection techniques at low redshift, but with the data that we do have, not with interpolating over data points that we don't have.
Right. So,
So that
excellent.
is where the three bands come from. So
Very
if you
cool.
scroll down, we should be able to see some results.
Okay. Isolating polymer bees.
Lovely. Okay. Great. So these are some of our resulting candidates in CEERS that we found using this method. So we took all the galaxies in those wedges, we ran
Mm-hmm.
them through some SED fitting programs, and we were able to pull out the galaxies that fit our criteria. We show, right, some redshift distributions, some
Right.
specific star formation rates.
Right.
um, a couple of extreme examples on both ends there. You have some supposedly very quenched galaxies. You
Yeah.
also have some supposedly higher redshift quiescence. Right. Yeah. Yeah. Then that actually aligns quite well. If you recall back to the original plot with the templates, that aligns quite well with the high redshift template
Yeah.
we were
Okay.
showing.
Okay.
And so it's not too far off. And then on the far right,
It's
we
like,
overlay again some observational data of different kinds of galaxies. So the purple
okay.
are a sample of generally red galaxies in CEERS. So that can be dusty, that can be quiescent. These were photometrically selected, so you can see they kind of span all over the space. The pink solid circles at the bottom are the very, very high redshift candidates, the ones that in
Hmm.
theory with emission lines
Yeah.
could contaminate. Thankfully, they don't.
Right.
Um,
Right. We're near. Yeah.
yeah, yeah. And let's see, the triangles are from another paper that used a different method to find quiescent galaxies in the same survey. So
Okay.
again, testing, how much overlap do we have?
Good.
Pretty good
Good.
overlap.
Yeah.
Yeah. And then the red kind of, what are those? Trapezoid?
SMGs.
Yeah, there's some millimeter luminous galaxies, another phrase for very, very dusty
There you
galaxies. So you
go.
can see most of them lie outside of that wedge.
Outside of our
hmm
bounds.
And then green X's, yeah, those correspond to yet another sample of quiescent galaxies from another paper.
Uh-huh. And most of
Again,
those lie in the band as well.
pretty good. Yeah.
Good.
It was pretty solid. I mean, we did have the problem here is definitely high contamination. That's a common issue with all of these. This paper does not solve that problem.
Okay.
But this paper does have a more empirical, or this approach is more empirical in the approach and selection. So our
Mhm.
contamination is still high, but the selection is a little bit more robust, in my opinion, because we actually have the observations to constrain it.
Right.
Um,
Very
and
good.
so, yeah, I think I actually show a little bit of details in the appendix. Maybe we can jump down there.
Sure.
The
As long as we're
conclusion.
talking contaminants, let's jump
Yeah.
into the appendix. And here we go. The red selection wedge.
It's this one,
Okay.
that's right.
Yep. Hmm.
So yeah, you can see some
Ah,
contaminants in each of the, let's see, here we go. Wide and red. Okay, so these are additional quiescents that were found, yeah, in the wide and you can see that red dash line. That was a
yes.
third option, but has even higher contamination because we know that SMGs or dusty galaxies are
Right.
there.
Right here.
Yes, and so you can see the point in this figure was to show that the yield was really low for these galaxies. So we didn't consider that as a very important addition in the main text.
Right. So you get a little bit of signal for a whole lot of noise,
Exactly, exactly,
basically.
exactly. And then if you scroll, you can see it in the figure below, the amount of
Uh,
noise.
oh, yes, there you go.
Mhm.
Uh-huh. In fact, that's worth looking at altogether.
Mhm.
So you get a sense of that.
Exactly.
Here you go.
So you can see on the left-hand plot, it's a lot of star-bursty galaxies. That's what that specific star formation rate
Yep.
is showing us, that dark blue or teal.
Hmm.
Intermediate redshift. So the redshift range isn't too far off. Maybe some low redshift dusty galaxies. Yeah,
Yeah.
nothing too too surprising. And then the attenuation we show, so the rate of dust absorption and how that continuum gets reddened, you can see how it jumps pretty much along that black line
Yeah,
from
it does. It
little, yeah, right?
almost adheres to it like a boundary.
Yeah, yeah. I found that really, really neat to see in
Hmm.
the data.
That's curious. Okay.
Hmm. And so, there's still some things that pop over on both sides, but for the most part, it's pretty strong,
Yeah.
that delineation. And you can also see how, again, that deeper dashed wedge has a lot more contamination as well than the solid lined wedge.
Yes. Yes. Yes,
Mhm.
definitely. Uh-huh.
Yeah.
Okay.
So with this sample, if you scroll up to that table,
Let's slide on up and save figure two and table. Here we go. Oh, so we got 44 of these. Okay, very good.
yeah, so we have 44 candidates. And what I just show very briefly in that far, far column
Mm-hmm.
called Other Selection Methods just
Yep.
shows which of these would be selected by some traditional and some new
Ah,
selection
okay.
techniques.
Okay, good. Cool.
So
Okay.
the ones A, D, and G, those are the newer ones that are similar to this selection technique that have been adjusted as well to identify high redshift younger quiescents. But the UVJ is the one that is anchored on low redshift studies
Yeah.
and is not quite as successful in identifying these sources.
Okay.
So yeah, you can see quite a few
Yeah.
match, but quite a few don't. And then I think I have this in a visual figure. Yeah, you can see some red shifts. They're all quite massive. There is still work to be done to verify these
Yes, you
sources for sure.
are.
Um,
Yes, you
and then I think if you scroll down, I think I visualized
got to
some.
visit that.
There
Yeah,
we
there we go.
go.
Yeah, yeah. Okay.
Yeah, so on the right-hand side, I'll just show very briefly, this is the UVJ figure I was explaining that, again, just doesn't do as great of a job. So traditionally, all quiescent galaxies should be in one of those upper left wedges, um, maybe extending a little bit down. There's a tiny dotted line in the
Yeah.
bottom corner, right? That's the post-starburst line defined at lower redshifts.
Mm-hmm.
Um,
Okay.
and so, in theory, they should all be there. But again, the J band is not constrained without MIRI data. And so, it is hard to know whether or not this figure is appropriate, this approach is appropriate, are my selection techniques more robust, or should this be revisited with MIRI data, which is definitely a next step.
Yes. And we'll come back to that.
Yes. And then on the left-hand side, we show a
Okay.
number density figure, which is pretty common with these samples because we're curious. In general, we found more than we expected in a cubic volume
Okay.
as a function of redshift. In
Okay.
general, we find more than expected
Um,
um, across the literature, not just in this paper. And this was just demonstrating that that is still happening here. And we do see quite a few, that's right. Yeah, the solid and dash lines show some
Model.
simulations.
Yeah.
And there's some really great papers out there that have come out since this one, doing
Oh,
a lot of analysis on why some simulations struggle to produce these galaxies. And it has to do with a lot of extremity. Forming a lot of stars in a short period of time is hard.
right. Right.
And so that's where a lot of it comes from. And these galaxies are rare, so maybe their cosmological boxes aren't big enough. It just depends on the simulation.
Okay.
But in
Okay.
general, we
But either
find,
way.
yeah, yeah, right. I mean, sometimes about an order of magnitude
Yes.
or more off,
Yes.
right?
Easily.
Yeah. And so that's what this figure is showing, that this kind of tension is still present and important to understand why it's there. Some simulations, it's not, again, even though they don't produce them in enough populations, it is still great that they produce them at all. Some can't even produce them at all.
Yeah, okay,
Um,
well, that's a problem.
yeah, yeah, yes. So we're happy
They
with
don't
the fact
exist. They don't exist.
that, yes,
Don't look. Don't look.
don't look. And so, yeah, so we're happy that some produce them at all, even if it's not in the amount that we expect to see.
Okay,
Um,
Chris, let's go.
that's right. And a big part of that is, understanding, right, forming a lot of mass in a short period of time, but also quenching a galaxy in the early universe is difficult. A lot of simulations kind of have this turn on, turn off toggle for AGN, for active black holes.
Yes.
Um, And while AGN are likely part of that, we've not seen observational evidence that's proven that they
That
are the
correlation not
explicit.
real strong. Yeah.
Exactly,
If at
exactly,
all.
exactly. And so I think it's going to take a lot of fine tuning for more nuanced approaches for understanding physical processes in the ISM, things like stellar feedback and stellar outflows, and maybe looking at environments also. There's recent simulations that argue that some of these sources are not in overdensities, but are instead quite isolated, perhaps maybe drying up the cosmic web
Yeah,
near
yeah,
their
yeah.
node. Yeah. So understanding exactly, what environment, what flows are happening into the galaxy, are smaller galaxies bringing in more gas and causing little bursts of star formation, those sorts of things will be very, very important and require really, really large samples. Again, hence this paper.
Oh, I'll come back to that point. Okay. Very
Yeah.
cool.
So yeah, as
Excellent.
far as future work goes,
Ooh, let's hang on to that. Hang on to that.
yeah.
Did I
So
cover one more? Did we cover that one? Oh, yeah, we
yeah,
did.
we covered that one. We covered contaminants. Oh, this one. Yeah, this was just me describing the simulations again. It's a pretty
Mhm.
brief section because the the differences in simulations is huge. It can make its own paper. And in fact,
Yeah,
someone did recently publish their own paper comparing all the simulations and quiescent galaxies within. Um,
excellent.
so I definitely recommend you go read that. It's Claudio Lagos wrote that paper, I believe, last year.
Good shout out. Okay.
Um, so yeah, so it's a wide diversity. We're not entirely sure why some do and some don't. We posit a couple of ideas. Some are semi-analytic, some are hydrodynamical. So those, semi-analytical models often come from existing empirical data, and so they tend to do a little bit better than the hydrodynamical ones, but not always.
Right.
So
Okay.
yeah,
Got our work,
um,
got our work cut out for it, which I'm going to come to.
yeah,
Cool. Very cool.
yeah. We
All
can we
right.
can move into that.
Very good. All right. Ariana, I want to thank you so much for walking us through your very awesome article.
Thank you.
Nice. Thank you
Appreciate it.
so much. The hunt for
The
quit.
hunt. The hunt is on. And so, yeah, so some of the future stuff we're doing is trying to verify this, yes, using MIRI data.
Okay, good. Yes.
Now it exists over a lot of these surveys, which is great. So checking in on that and seeing if the J-band can still be used with MIRI data. And even if it can, is it possible that we still are finding and excluding those younger, maybe dustier
Mm,
quiescent galaxies?
right. Yeah, that issue doesn't go away.
No, it does not. It does not. There have been a couple of papers recently, again, census papers come out that have explicitly found dusty quiescent galaxies at high redshift that do kind of defy some of these techniques. And so it's been fun to see that come out. And I am running a little self-promotion. I am doing a little bit of work on cold dust in quiescent galaxies using some ALMA data to see if we can actually quantify how much dust is present and then kind of extrapolate how that impacts our selection.
Ah, right. Okay.
Hmm.
Good.
Hmm.
That's pretty mild self-promotion.
Yeah. Yes.
Okay, so you kind of went there a little bit. Particularly, are there other wavelengths, perhaps? Are there other facilities that may be coming online in the relatively near future that could help increase the sample size? So tell me what it would get to get instead. We have 44 in this.
Hmm.
What does it take to get an order of magnitude more? What about
Yeah.
right?
Yeah, so a big part of that is definitely just the rarity in and of itself. So you need bigger
Okay.
surveys.
Okay.
So I am also part of Cosmos Web, which is a much bigger survey.
Right.
And we have a sample of 100 to 300 galaxies, depending on how you define it. Um, and that factor of three is well within uncertainty, which is so frustrating for sometimes doing, math in log space. The uncertainty is significant.
Yes. Yes.
And so we have a larger sample, which is really excellent. We do need bigger surveys. We do need longer wavelengths. We need more MIRI coverage,
Yeah.
uh,
Yeah.
which is more expensive than NIRCam coverage. It's not quite the field of view is smaller, so it takes more time to do the tiling.
Yeah. Yeah.
Mhm. As far as other facilities, yeah, so again, we have high contamination. And the problem with CEERS is it's in a part of the sky that's very difficult to follow up with ALMA, which is good at kind of ruling out those
Right.
those
Right.
contaminant dusty galaxies. And
Uh-huh. Mhm.
I'm focused on Cosmos Web because
Okay.
we have a lot of ALMA data on these all over the sky, including some nice contiguous maps that are really, really huge
Okay.
that we can use to rule out some contaminants.
Good.
Um, which is very nice. So that's Alma synergy is really, really important. As far as like Ruben and Roman, those are a little bit too blue.
Yeah.
So not quite as helpful, but they might be helpful for understanding any lingering star formation in the galaxies. Maybe
Yeah.
some
Catching the bleeding edges of the distribution, if you like.
Exactly. Yeah, 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 exactly. If you're looking for those galaxies that are in that transition phase, those would be really, really important. And especially because both of those are going to be great, big survey imagers. And so there'll be a lot of really rich data for understanding the environments of these sources too. There's recent work coming, or that's out, and then also coming up, looking for tiny, tiny blue satellite galaxies around these high redshift quiescents, which we've never had the capability to do before. And we're finding potentially in excess, which again impacts their evolution. And so that is what those blue telescopes can do, which is really nice.
Well, we're going to have to appropriately name them to little blue dots.
Let's not start a huge controversy now.
Oh, why not? Stir the pot, stir the pot.
That's right.
Good idea. And we won't even get into, what's needed on the simulation side. I assume they know what their problem
They
is.
know what their problems are. I have a lot of collaborators and friends in that community, and I'm regularly messaging them. That is why it's good, if you're an observer, a budding astronomer observer here, make friends with simulators so you can bug them
And
to,
vice versa, I will say, right?
yeah,
If you're a theorist, if that's your thing, try and tie it close to the data.
agreed.
It's
Yeah, we
always a
need to
good
be
thing
able
to
to
do.
test each other's work, our hypotheses.
Hmm.
We need to bug each other more and work together more. And so yes, I have a few collaborators who I'm regularly asking questions and claim they're working on things. And I do also hear part of it is a technology issue, just having the physical computing space to
Yes.
do those physics. Yeah.
Yes. Very cool. Well,
Yeah.
to me, I think it's going to be really exciting over the next couple of years, half decade or so, as this field develops a little bit more. We get some more samples. Yeah, it'd be really exciting to see this develop, and we can start piecing together these strangely quiescent galaxies between 3 and 6 redshift. So yeah,
I agree. Yeah, I agree. I hope in the next, 5 to 10 years, we can come up with some creative tests for understanding their quenching pathways and things like that. Right now, it's very difficult to do.
yeah.
But I think it just takes more creativity and us coming together as a community.
I hear in places where summer is defined by a lack of rain, that's where a lot of creativity comes from.
That's right. Yeah. That's
Just a
if we're
loop.
inside,
Just a loop. Yeah, that's right. So
yeah. So the time where most people in the Pacific Northwest, you cannot find them at their desks. So we'll
yeah,
see.
it does. The rain doesn't bother anybody. They just put their ponchos on and go, right?
It's so true.
Very cool. All right. Ariana, I want to thank you so much once again for walking us through your very awesome article. Thanks.
Thank you.
And that will do, everyone. And I hope this made your astronomy day and your quiz and galaxy day just a little bit better. And we will see you on the next one. Bye bye.